Alright, let's start it. Do you hear me? Can you write in Discord that you can hear me? Once again, do you hear me? Oh, thanks. Alright, so you know from nowadays so-called online teaching at the university, so of course this lecture will be online as usual, but also the seminar will go to this platform, so I will send you the smart table and the presentation, and we will keep in touch in Discord. Alright, let's go for the lecture. This is example you can solve it, but at first go through the new topics. We will talk about energy. Energy, work, potential, these are similar things. You will see why. At first, let's define the energy. Energy is nothing else, just the so-called path integral of the force. What is the path integral of the force? So look at the PDF, for example, if you push a box with the force something, let's say 100 Newton, and if this box moves, you will do some work on this box. The work is nothing else, just the multiplying the force with the displacement. If the force and the displacement are parallel, and if the force is constant during this motion, that's the simple F times S, what you learned before, I'm pretty sure. What will do the work? The work is energy transfer. The work will change some kind of energy of the object. If there is no friction, the work will increase the kinetic energy. If there is friction, some part of the work will increase the kinetic energy, and some part of the work will heat up the surface. You see here this red part on the presentation. What are the differences between internal energy and kinetic energy? So we can say the kinetic energy is something you can transform to anything. So, for example, you can transform it to potential energy, but the heat is a special one, because heat is nothing else, just the statistical motion of the particles in the body. It's pretty hard to get it back, but there are, of course, solutions for that, but not for increasing the surface with, let's say, 1 or 2 Celsius, but for higher temperatures. This is the power plants. So internal energy is related with the statistical motion of the particle in the body. Kinetic energy, what we learned before, this is 1/2 mv square. This is something that's related to the mass and the speed of the body. And there is a third type of energy we will learn. This is the potential energy. So it's nothing else, just the fact that in a system, I can draw you, if we define a potential equals 0, in this system, if the body is here, it has no potential energy. If the body is here, the potential energy is something. So the potential energy is related to the configuration, to the position of the systems. Similar story is the spring. even the bodies here or there, and let's say in both cases the V equals 0, it has no kinetic energy. Let's suppose there is no internal energy, but because of the position here or here, it has some potential energy. So potential energy related to the configuration of the system. Alright, let's see another point of view about potential energy. So potential energy is the energy, let's see the gravitational potential energy. Here we have a body at, let's say, 1 meter, and there is a weight which is technically the gravitational force, and since this body will move, let's say 0.1 meter, and this displacement and the force, they are parallel, and since this force is constant, the work, the work done by the gravitational force on this box by moving from 1 meter to 0.9 meter, so the delta R is 0.1, that will be F times delta R. And in this case, if the mass is, for example, 1 kilogram, this is 10 times 0.1, this is 1 joule. And this is the potential energy, the energy stored by the configuration of the system. So if, for example, from 1 meter I move to 0.9 meter, the work done by the potential energy, done by the gravitational force is 1 joule. That means you lose something from the potential energy, and this amount is the change of the height times the gravitational force. So in this case, when a box falls down or a ball falls down, the gravitational force does work on the body. That means it will increase the energy. So this is a plus. You can see by the direction of the forces. So since they are parallel and point in the same direction, the scalar multiplication of the two vectors will be positive. It means the gravitational potential will be smaller and the energy of the body will be larger. So in this case, there is no friction. The changes of the potential energy, the work done by the gravitational force of the box, will increase the kinetic energy. And this is a pretty simple example. So let's calculate something. For example, here we have the zero level. For the potential, we always need to know where is the zero level. And let's say we have a 3 kilogram box on the height 3 meter. What is the potential energy? The potential energy is the work done by this external force by moving from the initial position to the zero position. This is the weight is 30 Newton. The displacement moving from 3 meter to 0 meter is 3 meter. So the work, since the displacement and the weight points in the same direction, this is 30 times 3, this is 90 joule. So what we can say, in this position at 3 meter, the potential energy of this box, this is the result of the configuration of the system is 30 Newton. So how will, let's suppose at the beginning the v equals 0, how will the speed change, since the work is energy transfer, and in this case we can only change the kinetic energy. This is the kinetic energy in the final position minus kinetic in the initial position. Since at the very beginning the v was 0, this is 0. So the work, which is the changes in the gravitational potential, will be the final kinetic energy, which is 1 over 2 mv square. If we go back here, so this 30 is m times g, and this 3 is h, we can see mgh, which is a well-known formula, will be the 1 over 2 mv square. That means if you multiply with 2, 2gh will be equal to v square. If we take a square root, this is the v the box will have when it reaches the 0 level. We can solve this example by calculating the acceleration, calculating the initial velocity, initial position, and so on. What are the differences? And the differences between kinematics and dynamics. Let me clear the table. So this example we can solve kinematics and dynamics. So for example, if this is the 3 meter, falling down is nothing else, just a one-dimensional motion. Let's say this is the x-axis and this is the 0. So at the beginning there is the initial speed, which is 0, there is the initial position. In this case, since the x goes downwards, it's minus 3 meter. We know the acceleration is g. We can calculate the delta vt, which is the integral 0 to t g, and also the delta x, which is the integral 0 to t v. And if we know the xt, when it's equal to 0, you can calculate the, just a minute. Alright, so you can calculate it in the kinematics, and in this case you will have an xt and a vxt, which means at any time you know what is the v and what is the xt of the body. What is the differences when you use that very simple mgh equal 1 over 2 mv square, which said the changes of the potential energy will increase the kinetic energy, 2gh. In this case, you only know what is the final v, and you don't know anything what's happened with the body, for example, at 2 meter. You don't know the time when it goes through the 2 meter level. You don't know the v and so on. So you don't have this xt vt function. So only if you need to know something in the initial position and at the final position, you can use these formulas. Otherwise, if you also want to know how the box moves, you have to do the longer way, integrate, boundary condition, and so on. That's a powerful and fast solution to solve the examples. Alright. This gravitational potential energy only depends on the height of the object and does not depend on the path, how it moves. So for example, it can move like this, and the V will be every case the same. What does it mean? This means we do not have to worry about the path, we only have to calculate with the initial and final position in these gravitational forces. It's not true for all the forces, it's true for example, the gravitational forces, the Coulomb forces, and all the forces which have this 1 over r square formula, and all the forces which is a constant force, which is the gravitational acceleration close to the surface of the Earth. There are forces, for example, Lorentz forces, which is not conservative forces. It's said in that case it's not too easy to calculate with, but of course there are method and also program to calculate that. Alright, what is magnetic energy? You know, the kinetic energy is nothing else, just solving, you can check in the previous presentation, just say that the work is the force path integral. If you replace the force with m times a from the point A, point B, and this is the previous presentation, it will give you VB square minus 1 over mVA square. So you can get this kinetic energy by only using the definition of the work and the Newton axiom. The potential energy is observation that depending on the configuration of the system, there can be energy stored by the configuration. If we add these technically artificial formulas, you can have a so-called mechanical energy. Why the mechanical energy is important? Because if you have a system where there is no friction, for example, no external forces, in this mechanical system, you can say this mechanical energy has to be constant. You can see in the picture on your upper right, if you have a small car, if you go up to a hill and then down, this kinetic energy plus potential energy will change during this path, but the sum will be the same. So if there is no external forces that could increase any of the energy, potential or kinetic, if this is a closed system, the mechanic energy has to be conserved. But you can extend this view. So for example, if you have also a battery and an electric motor, you can speed up the small car, and if you can transform the chemical energy in the battery into kinetic energy, and then if you can transform it back without any loss, this energy also can be, the sum energy also can be a constant. Another simple example for potential energy is the spring. We have a energy, we can have an energy stored in the spring which is 1 over 2d, or in some book it's key x square, and the x is the displacement from the relaxed position of the spring. And also if there is no changes, for example, in potential energy, I mean gravitational potential energy, and there is no friction, you can say the sum of the potential plus the kinetic energy is the mechanical energy, and it has to be conserved if there is no external forces. Of course, when you push the spring, you are the external force, but if you release it from that second, it's an isolated system, since you release it and you won't exert any other forces, and in this case this potential energy plus kinetic energy will be conserved. You can also imagine any other situation. For example, you have spring, potential energy, kinetic energy, just up to you. In any case, the sum of the potential and kinetic energy has to be conserved. It's an isolated system, and there is no way to have any friction, because the friction somehow creates internal energy, and this internal energy you can't get it back. You can't transform it to potential and kinetic energy. Power, we talked enough about the work. Once again, work is the force path integral from A to B, and technically this is energy transfer. This energy will go somewhere, changes the potential energy, internal energy, kinetic energy. We can say, so since F can depend on T, V can also depend on T. The power is nothing else, just the derivative of the work. And technically, since delta V equal delta T, so this is the derivation of the energy change of the system. We still use horsepower as a unit, so it has a unit watt, but from historical point of view, we can also use horsepower, even in Europe, not only in the US. That has historical reason, because James Watt developed the steam engine, and the steam engine was used at first in coal mines, and at that time in the coal mines they moved the coal from the mine to the surface with horses, and James Watt said that I can give you a steam engine that's that powerful like 10 horses, and we had to define what is the power of 10 horses, what is the power of 1 horses, and by definition they said 1 horse can lift 75 kilogram coal with 1 meter in 1 second, and that's this 740, or in some case 46 or 50 watt. All right, let's go back to rotational to define what is the rotational kinetic energy. You remember, for rotation instead of displacement we use angular displacement, instead of velocity we use angular velocity, instead of acceleration we use angular acceleration, but the story is just the same. Do not forget that we will use radians. Its unit, or its common value, is the pi, which is 180 in degree. So the theta t, which is angular displacement, is given by rad, and omega, the angular displacement, which is by definition the time derivation of the theta. it's given by 1 over s. We also can use, instead of acceleration, the angular acceleration, which is the time derivation of the angular velocity. It has a unit 1s squared. Alright, so let's see what we have. We want to calculate the kinetic energy of the body that rotates about a fixed axis. We know the kinetic energy is 1 over mv squared. Oh, perhaps it's not that slide. Yes, this is the slide. This is the axis and it rotates. For example, this is a constant angular velocity rotation. That means it rotates like the wheel of the car when the car moves with a constant speed. The only problem using this formula for kinetic energy is that the v, the speed, depends on the distance from this fixed axis. So v1 equal omega times r1 and v2 equal omega times r2. So for a body, the v is not a good unit because it depends, the speed or the velocity depends on the distance of the body. Therefore, we should have a rotation energy which depends somehow with the omega, since this is the unit which describes the motion by nature, which describes the rotation by nature. So how can we do that? So you can divide the body into small, let's say, boxes, and let's say this is the 1, 2, 3, 4, and so on, and you should sum all the small boxes kinetic energy. That will need some simplification, so if you solve it, we will see that the rotation kinetic energy also depends on v squared and also has this 1 over 2, but instead of m, the mass, which is a good unit for translational kinetic energy, for rotational kinetic energy, we have to sum, oops, you can't see that, we have to create a sum over the mass and the points of the body. This sum is the moment of inertia. So see, the structure is the same. We have 1 over 2, we have something which is related to the body and something else in kinetic energy. This is v squared. In rotational kinetic energy is the omega squared. So 1 over 2 times something which describes the object and something that describes the motion of the object. In the kinetic energy, so same structure, but since in the kinetic energy we have only a mass, here we have, technically this is a three-dimensional integral. This is more complex. So this moment of inertia contains not only the mass of the object but also the shape of the object. Of course, we don't have to do that calculation for any object because we will use some simplification. For example, for a cylinder, it's 1 over 2 mr squared. For a ball, wait a bit, I can show you. So we have object where other people already calculated this integral. For example, a cylinder is 1 over 2 m r square, which is where r is the displacement. So for example, look, there is no parameter for h, and if there is a ball, is 2/5 mr square, and this is the r and this is the mass. So for mathematical objects, you can easily calculate the moments of inertia. Otherwise, if you have a more complex body and if its density is not constant, so you have more material here than here, unfortunately you have to solve this rho r square dv, which is technically, this is a three-dimensional integral x, y, z, or theta phi r, and you have to calculate it. It's not easy, but we won't use any complex example. We are mainly using cylinders and its density is a constant. Oh, here we can finish it. So, what we learned today: so work, by definition, the path integral of the force from A to B, where, for example, from A position to B position, you push a box, and in this case, the F can depend on anything, so you can push this box with a larger force in the beginning and smaller at the end. The work is energy transfer. This energy transfer can change potential, kinetic, or also the internal energy, which is technically the heat. If there is no, for example, friction, and there is no way to change the potential energy, which is the frictionless motion of a box on the surface of the table, the work only changes the kinetic energy. If there is no friction, but the potential energy can change something, like this example, frictionless motion of the box on a hill. In this case, we can define mechanical energy, which is the potential plus kinetic. And if this is an isolated system, which means there is no external forces, no force can go through this boundary, it has to be a constant. And that can be, this potential energy can be spring or gravitational potential energy. This energy conservation is very useful in some example. Since we know the kinetic energy is 1/2 mv square, if you have a box with the mass m, with the speed v, you can calculate easily. But if box is just a part of the rotating system, you have to calculate this kinetic energy for all the boxes. That's not easy, because the v is not a good value for rotating system. Rotating system, if it rotates the constant angular velocity, the omega is the good one, the most convenient one, and therefore from m over, so instead of calculating the kinetic energy of all the points, all the small boxes, you have to do something else. This contains the omega square, and if you calculate it, you will have like MI/RI square, and this is the moment of inertia with more precise. This is the volume integral of the rho times r square. It's very complex to calculate, but for example, for cylinder, it will be only 1 over 2 m r square and rn. That means if you want to calculate the rotational kinetic energy of a cylinder that rotates around its, how can I say, longer axis, what you can see here, this is nothing else, just this 1 over 2, and here we have this moments of inertia 1 over 2 mr square, and if this angular velocity is omega, you can write here omega square. So for simple objects, we can use pretty simple formula to calculate the energy. And for the next lessons, we will learn how to solve example for bodies that can not only translate but also rotate during this motion. Alright, that's all for today. I stopped the streaming and you can have questions in Discord, or we can say goodbye.